Every unit this semester has its pretty part of chemistry, kind of what we call descriptive chemistry, and then it has its numbers part of chemistry. And so the descriptive part of chemistry for Unit 1, we talked about, how you classify matter as pure or a mixture. And then we talked about, what else did we talk about? Properties, physical, chemical properties, intensive properties, extensive properties. And so now we need to kind of set ourselves up for talking about numbers. And the reason we need to talk about numbers in science is because we do measuring in science. And we, of course, when you measure something, you have, and we'll be talking more about this, but like if you measure a length, you have the number part and then you have the units. Okay, so that might be 1 foot. Okay, so we're going to have to talk about measuring things. We just got to do it. So one of the things that I think is cool is that all of the sciences across the board, biology, physics, chemistry, earth science, they all have to come back to the same fundamental units of measurement. So we need to refer back to some sort of standard. So within the different disciplines in United States, we also have to be able to talk across the world. So it all goes back to some reference standard. Mass, by definition, is how much, I think of it as like how much atoms are there in that chunk of matter you're talking about. That's the mass of that object. The length of an object is the distance between 2 points. Volume can actually go back to length. It's volume, though, is how much space something occupies. And I mentioned volume, we can use length to get to volume if we look at something like as in a cube, so it's got like length, width, and height, and so that's volume. Temperature is not the same thing as heat, and I think we'll get to talking about that this semester, but temperature is just kind of relatively speaking what direction thermal energy will flow. So it's kind of a subtle thing. Temperature is kind of a subtle thing, I think. So mass, the standard for mass, the standard to calibrate your scales, of course we measure mass on a scale, actually goes back to, I have a photo coming up here in a minute of a duplicate of this cool chunk of iridium platinum alloy that's under lock and steel in Paris. And I tell students that mass is so important. So, for instance, if you're buying pound bags of coffee, now, are we sure that's a pound, or is it a pound plus or minus 1 ounce? Is it a pound plus or minus 10 ounces? So those scales need to be calibrated and certified back to some standard, traceable actually back to this granddaddy standard. Length, actually, when we get out our yardsticks, now, of course, the more precise the length is, the measuring device is, the more precise any measuring device is, whether it's for length or anything, the more expensive it is. But length actually goes back to the distance that light will travel in a fraction of a second. So a light will travel 1 meter, exactly 1 meter, in this fraction of a second. I think that's kind of weird. It's not how I calibrate my yardsticks, but... Volume then goes back to length. Volume, if we go in a cube, we'll be talking more about this actually in one of the labs you're going to be doing. If you have something that is straight on all 3 sides, whether it's kind of got a rectangular shape or square cube, we can take length times width times height to get volume. So therefore, volume actually can go back to length. Time goes to the element cesium, and one version of cesium is an isotope 133. And actually, one of the things that we talked about earlier, probably when you told me about an atom, is that the outside electrons, every atom has electrons, unless it's, I guess, a hydrogen cation. But electrons on the outside of the atom, as they transition, they actually emit energy, and that's specific to the element they're transitioning. And so one transition of cesium will give us standard for time. Temperature goes back to absolute zero, which, if you're familiar with that, and we will talk a little bit about that, I think. Absolute zero is 0 Kelvin. It's where all molecular motion stops, which is kind of neat to think about. So basically, between absolute zero and the triple point of water, which is about 0 degrees Celsius, that is 1 Kelvin is that fraction of an interval between there. So I don't know. Amount in chemistry, we don't deal with like dozens of atoms and like packets of dozens of atoms. We deal in packets of moles of atoms, and we'll be talking more about this. But 1 dozen eggs is equal to 12 eggs. Okay, 1 mole of eggs is equal to, and it's so big we have to pack it up in scientific notation. We're talking about that coming up. But packed up in scientific notation, that many eggs is 6.022 times 10 raised to the 23rd power. Now that's a really big number. Okay, that many eggs is equal to 1 mole of eggs, the standard amount. So this is that fake. Actually, this is a photo of a fake. This is in the Washington, D.C., and the real one's in Paris. But there is the important little standard mass there for all of our mass measuring devices to be calibrated back to.